Welcome to the CAD Office training series for F.Connect for Open Bridge Modeler. My name is Heather Pier, and I'm a structural engineer with WSP USA. In this video, we'll be covering exercise 5.8 from the Bridge Design 3D Modeling and Plans course guide. This exercise demonstrates how to model a pier and bearings. Let's get started. In exercise 5.8, we'll start by modeling the pier using the pier template developed in exercise 5.3. We'll make sure that we define the materials which are used in the FDOT automated bridge quantity workflow. We'll also make sure that we assign a feature definition which controls the pier attributes. We'll then apply an elevation constraint which uses a terrain file to control the footing elevations. After that, we'll model the bearing elements. In OBM, the bearing assembly consists of three components. The second and the third are optional. The first component is the bearing, or bearing pads. The second component is a bevel plate, which in our case is required per the SDG, and the third is a bearing seat, or pedestals. In our exercise, we'll use all three. Again, we'll make sure that we define the materials and assign the feature definition. We'll start by opening the dataset file for 5.8 Begin. We'll make sure that we're in the FDOT workflow within the dataset workset. We'll go to Browse. We'll find 5.8 Begin. We'll click Open. If you've been working through the exercises in sequence, you're welcome to either continue with your bridge model or open the 5.8 Begin file. Our model is ready to place a pier. To do that, we'll go into the Home tab within the Open Bridge Modeler workflow, and within the substructure group, we'll click Place Pier. In the Place Pier window, we'll first select our template. We'll click the three dots or the ellipsis, and then we'll select the pier template that we created in exercise 5.3. We'll select _TR-pier, and you can see in the view window that this is our template that we want to select. We'll click Select, and then we'll make sure that the cap length adjustment is set to Aligned. So what that does is it makes sure that the center of the pier is aligned with the center of the deck. Otherwise, if you don't select Align, it will center the pier on the alignment itself rather than the geometric center of the bridge. Now we'll go through and assign materials. You'll notice that in the materials section, you have an option to add the material for every component that a pier template could have. So in our case, we don't have a concrete pad, but the material is still there. We'll go ahead and leave that one blank. For our cap material, we're going to use the pay item 040045, which in this case is Class 4 bridge substructure concrete. For the column material, we'll use pay item 400-425, which is Class 4 concrete, but mass concrete and substructure. Click Select. And then for our footing material, we'll also select mass concrete, Class 4. Again, we're not going to use concrete pad material because we don't have a concrete pad. Similarly, we also don't have a pile encasement material. And we'll go through and we'll select the pile material. So in this case, we are using 24-inch pre-stressed concrete piles. And that's just our normal pay item 0455-34-5. select. And now for the feature definition, by default, it's selecting end bent with concrete pile. So we want to make sure that we select the drop down and then we toggle it to pier with concrete pile. That's the proper feature definition. And you'll see that the name prefix changes when you do that. So now that we have all of our pier options selected, we can see that the cursor message is showing us to select a support line. So we'll go ahead and select the centerline pier 2 support line. If you had multiple piers that you were placing using the same template, you would be able to select multiple support lines at the same time. In our case, we do not have to do that because we've only got one pier. So I can go ahead and right-click or reset to end. You can see the next thing that it's telling me to do is data point to continue. So data point is a left click. And now our pier has been created. We can take a look at our pier in isometric as well. So to get out of the Place Pier tool, we can go ahead and right-click or reset. We can open up View Window 2. We can go to the View tab, select Tile. Now we can look at our bridge and our pier in both wireframe top view as well as in isometric. Looks like everything looks good. So now we're going to set our elevation constraints for the footing based on the terrain file. Before we set our footing elevation constraints, we'll want to make sure that the terrain file is active so that it can be used to set the elevation constraints. In our references dialog box, we'll toggle on the terrain file, which is in reference slot 3. We'll zoom out. Now we can see the extents of the terrain file here. And then in the Home tab in the Bridge Setup area, we'll select Terrain. And then it asks us to locate the terrain model. So we'll click on that terrain model. And now it's set active. So you'll see when we set that terrain model active, if you notice, the footings adjusted a little bit. So it did that because the footing elevation constraints by default are set to 0 feet from the DTM. So it basically brought the footings up to be exactly in line with the terrain. So now that we've set the terrain model as active, we can go ahead and set the elevation constraint. So there's a couple different ways that you can select the pier in order to adjust the elevation constraints. You can either select it in the view window itself, so you can do that in the wireframe on the left, or you can do it in the isometric view on the right, or you can select it from within the Explorer window. We'll go ahead and select it in our top view here. Then you can see that there are various sections here. You want to make sure that they're all expanded. And then in order to access the elevation constraints, you'll go to the elevation constraints area. Click the area where it says select to edit. Then we'll click on the 3 dots. And it opens up the elevation constraint dialog box. So there are 3 tabs on this window. We've got the cap, the footing, and the piles. So you can set elevation constraints for either the cap, the footing, or the piles. You can do it for all 3 if you would like. In our case, we're just going to set the elevation constraints for the footing. So I'll click footing, and you can see by default it says from DTM and 0 feet. The other option is an elevation. If you wanted to just key in a hard entered elevation, you could do that. But in our case, we're going to let it use the terrain file. But instead of the default of 0 feet, we're going to enter in -3, so -3 feet, and click Apply to All. You can see here, this is letting us know that the reference is to the top of the footing elevation. So now when I click OK, our footing will adjust downward to be 3 feet under the terrain file. And in the latest version of OBM, the elevation constraints are set off of the minimum elevation, so it should calculate the footing elevation in the same way that we do. It takes whatever the minimum terrain elevation is and subtracts 3 from it. So we'll click OK. You can see now that our footing elevation adjusted and the column elongated in order to have that footing elevation be honored. And since we set this bottom portion of the column to be the portion that gets adjusted, the top portion stayed the same and the bottom portion adjusted. Now we're ready to create our bearing elements. We'll place the bearings at the end bends first. To access the Place Bearing tool, make sure that you're in the OpenBridge Modeler workflow in the Home tab, and then within the substructure group, we'll click Place Bearing. In the Place Bearing window, you'll see that there are 3 different sections that pertain to various bearing assembly items. One of them is the bearing, so that's the bearing pad itself. Another is a grout pad / bevel plate, so that's if you have a beam with a longitudinal grade over 2%. Per the STGs, you have level bearing seats or pedestals and a bevel plate to accommodate the longitudinal slope. And the last one is the bearing seat, which is also known as the pedestal. For our case, we're going to change the bearing type from cube to cell. So within the FDOT Connect workspace, we have built in FDOT standard neoprene bearing pads. An advantage to using the cells is that it's easy. You don't have to think about what the dimensions are in terms of the dimension conventions. However, it is not currently compatible with the FDOT Automated Bridge Quantity workflow in FDOT Connect 2023. FDOT is coordinating with Bentley to accommodate this in future releases, but just keep that in mind if you choose to go this route. Alternatively, you could use the cube option, or you could use a cylinder option if you're not using a standard neoprene bearing pad. You can use either of those. In this exercise, we're going to use the cell option. So we'll select what cell we are using, and you can see when you click that, there are options for the FDOT standard bearing pads. We'll select type H in our case, and we'll click OK. We're not going to change any of the active angle or scaling information, but we are going to change the orientation from pier to girder. We'll select bearing pay unit as volume, because rather than paying for bearing pads as in each item, we pay for them in cubic feet. Next, we'll check that the bearing assembly does include a pad or plate. In our case, it is a bevel plate. Our pad thickness will set to minimum thickness, and then our pad minimum thickness will give as 1/2 inch. And then we've got these variables here, this D1, D2, W1, W2. So these variables can be kind of difficult to recall, so it's always helpful to go to the Help tab, click Help Contents, open up the OpenBridge Modeler help document, and then you can either search for bearing in the search terms, or you can go Modeling, Substructure, Place Bearings, and then just open up the Place Bearing tool. You can see in the grout pad group, which is the same as the beveled bearing plate that we're using, and it has a schematic here where it defines the D1, D2, W1, and W2. So you can see based on the head station, so up station, W1 is the width to the left, W2 is the width to the right, D1 is the depth is what they're referring to it, and that's back station and D2 is a head station. So with that in mind, we'll fill in the information here. So in our case, they are both half a foot, 6 inches, D1, D2, W1, W2 is 1.5 feet, 1.5 feet, and the pad orientation is girder. And we'll go ahead and change this to volume. In our case, the bevel bearing plates are paid as a weight of steel, but we'll go ahead and select volume. Now we'll check has bearing seats. These are the pedestals. We'll go in and enter the pedestal information. This is similar D1, D2, W1, W2. So we'll want to set our minimum seat thickness to the FDOT standard 4 inches. So we can do 0.4. Then we'll define our D1 as 1 foot, our D2 as 1.5 feet, and then our W's as 1.75 feet, 1.75 feet, or 1 foot 9. Then we're going to keep our seat orientation as pier. The next thing that we're going to enter is our pad or path offset. So we're going to have a back offset and a head offset. For the back offset, since it's going to be our end bent 1, we'll just keep that as 0, and then our head offset is going to be 1 foot 6 inches. So our bearing line will be 1 foot 6 inches offset from our support line, which is in line with our front face of back wall. For our pad or plate material, we'll click the 3 dots, and then we'll go to the steel tab up here. So by default, it'll likely be open to concrete. If we click steel, now it'll give us the option to select steel materials. So in this case, we are just going to use grade 50 steel. So that's pay item 46022. We'll click select. For bearing material, we're going to use the neoprene bearing pad, so that'll be in the miscellaneous tab here. Neoprene bearing pads composite, that's pay item 400-147. Click select. And then for the bearing seat or pedestal material, that is just the same concrete that we're going to be using for the cap. So we'll go ahead and select the 400-45, which is just a bridge substructure class 4 concrete. Click select there. Then our feature definition is already correct. It'll be the neoprene composite feature definition. So now that we've got all of this information entered, you can see that our cursor is telling us to select the support line that we want to apply it to. So we'll select the front face, back wall, and bent 1 support line by left clicking. So you could add bearings to multiple support lines at the same time, but in this case we're just going to add it to 1. So we can go ahead and right click or reset to end. And then we're going to data point or left click to continue. You'll see it's now creating the bearing pads, as well as the bevel bearing plates and the pedestals. So it's going through and reprocessing the model to insert that information and those elements in between the end bent and the beams. We'll take a look, and it looks like we now have our bevel bearing plate, as well as our neoprene bearing pad and our concrete pedestals. So that all looks good. So next, we will add the bearings to the end bent 3. So for end bent 3, the pedestals are not going to be placed using the place bearing tool because the pedestals are built into the parametric cell. So we will again navigate to OpenBridge Modeler Workflow, Home tab, Substructure Group, Place Bearing. So we'll go ahead and untick Has Bearing Seat since we don't need to apply it. And then the information will be similar for the bearing pad itself, as well as the bevel plate. We're going to have a different path offset since this is end bent 3. We'll have a back offset of -1.5, and we'll have no ahead offset because this is an end bent 3, so there is nothing ahead of it. We'll have the same materials. In our case, we're not having a bearing seat, but it doesn't matter if we have the material defined. Since there's no bearing seat within this bearing assembly, it won't assign it anywhere. So now we'll go ahead and select front face back wall end bent 3, left click, and then again, we're only adding 1, so we'll reset to end, right click, and then data point or left click to continue. All right, you'll see that we now have our bevel bearing plate as well as our neoprene bearing pad, and then we have the pedestals already built into the parametric cell. This blue element here is just a piece of the parametric cell. It should be a non-plotting level, so you can turn it off, but we will not worry about it for now. So the last thing that we're going to do is add our bearings to the pier. So again, OpenBridge Modeler Workflow, Home tab, Place Bearing. So for the bearings, again, we're going to use the same bearing pad itself, the type H. We're going to have a bevel plate, the same dimensions, same type of bevel plate. And in this case, we are going to have bearing seats, so we'll check Has Bearing Seat again. And then for the dimensions of the bearing seat, we'll keep the minimum thickness of 4 inches, but we'll have seat D1 be 11.5 inches. So 0.11.5. D2 will have 11 inches, so 11. And then we'll keep the width as 1'9" for W1, 1'9" for W2. For the back offset, we're going to have -.11 inches, and for the ahead offset, we'll have +.11 inches. Every time that you have a negative number, that'll be back station. Every time you have a positive number, that'll be a head station. We'll keep the same materials applied and the same feature definition. So now we'll left click on the support line, and you can see when you left click, it gives you a temporary view of the bearing lines as well as a dot to represent the bearings themselves under the beams. So we'll go ahead and reset, right click, and then we'll data point, left click. And we'll let this go through and reprocess and accommodate the bearing assembly. All right, you can see now that again we have added our bevel bearing plate here, our neoprene bearing pad here, and our concrete pedestal here. So now our bridge has a pier added to it, as well as bearing assemblies at both end bents and the pier. Thank you for watching this section of the training series for FDOT Connect. Additional training videos and course guides are available on the CAD Office Training webpage, which may be found at fdot.gov/CAD.